In example 2, we want to determine our output voltage of the bridge amplifier shown below. The bridge refers to our resistors R1, R2, R3, and R4 connected in a diamond pattern with their voltage source existing between R1, R3, and R2 and R4. To begin, we will apply our ideal operational amplifier equations. That is, V1 will be equal to V2, and I1 will be equivalent to I2, which are identically equal to 0. For us to begin, we want to simplify our bridge, i.e. we want to relate our output to our input voltage within our system. To do such, we'd like to replace our bridge with a Thevenin equivalent. By doing such, we'd have a voltage source and a resistor in series such that we can determine our voltage at our input. To determine our Thevenin equivalent, we'll first determine our Thevenin resistance. And to do such, we short our voltage source within the bridge and determine the equivalent resistance between terminals A and B. We recognize that R1 and R2 exist in a parallel configuration, and R3 and R4 exist in parallel configuration. The equivalent of R1 and R2 is in series with the equivalent of R3 and R4, such that our Thevenin resistance is equal to R1 times R2 over R1 plus R2, plus R3 times R4 over R3 plus R4. To determine our open circuit voltage, we want to determine the voltage potential between terminals A and B. To do such, we have to determine the individual voltage drops across R2 and R4. And to do such, we'll express this in terms of node voltages. That is, our voltage drop between nodes A and D is the voltage drop across R2, which is in series with R1 being fed by our voltage source, such that VA minus VD is equal to R2 per R1 plus R2, and this quantity times our source voltage. Now to determine the voltage drop across terminals B and D, i.e. our voltage drop across resistor 4, recognize R4 is in series with R3 being powered by our voltage source V sub S. That is, VB minus VD is equal to R4 per R3 plus R4 times the quantity V sub S, which allows us to express VD is equal to VB minus the quantity R4 per R3 plus R4 times our source voltage. Therefore, we can insert VD from our second series voltage division into our first expression for series voltage division. Thus, we would have our voltage drop in terms of VA and VB. Making that substitution, we'd see our open circuit voltage would be the quantity. Now we can insert this Thevenin equivalent back into our amplifier such that we'd have VOC and R Thevenin. Now to relate our input and output, we'd want to construct KCL at node A. In doing such, we'd have I1, I6, and I out exiting. And we'd have no current entering. That is, I1 plus I6 plus I out is equal to 0. From our ideal operational amplifier equations, I1 is equal to 0. Or if we apply Ohm's law to this particular KCL equation, we'd have I6, which is VA per R6, plus I out, which is equal to VA minus V out per R5 is equal to 0. Expressing this in terms of our output voltage, we'd have V out is equal to the quantity 1 plus R5 per R6 times VA, where VA is going to be equal to VOC. For I1 is equal to 0, and there is no voltage drop across our Thevenin resistance. Thus, inserting our expression for open circuit voltage for VA, we'd have our output voltage is equal to 1 plus R5 per R6, this quantity times R2 per R1 plus R2, minus R4 per R3 plus R4 times our source voltage.